Què tal? Bona tarda. I switched to English. We have some visitors, so hopefully it's okay for everyone. Hi, good afternoon, evening. I'm Daniel from Schibsted, who is kindly sponsoring this latest meetups. And I'll be very brief, just introduction of what we're going to do today. Basically, we go over the DockerMaze challenge, which is a technical challenge some of us have been enjoying the latest days, and we'll have Mark and Gerard explain a bit the architecture of the DockerMaze challenge, as well as the solutions. And then there'll be some small prizes from for some of the scorers. And yeah, and also just a brief word from the sponsors. So Schibsted, as you probably know, is setting up a big team in Barcelona, and also Oslo, Stockholm, London, etc. So we're obviously hiring, as you know. So if you're excited about this kind of stuff, we'll be around after refreshments. So please chat up to us, and we'll happily tell you more about what we do. And to remind you that there'll be the prizes ceremony at the end, not very fashionable one, but still quite nice. So without further ado, I will leave it to Mark, which is another colleague in Schibsted, to explain the architecture. Hope you guys have fun, and if there are any questions, probably at the end we can answer anything you like. Okay? Thank you.
Hello, everyone. I will try to be as short as possible, because the intention of this meetup, even if it's for the microservices stuff, it's to present the solutions of the DockerMaze. So I will explain a little bit what we did in the background, or in the behind the scenes. So in the last DockerCon here in Barcelona, we created a challenge for the people attending the DockerCon, and it was about solving a maze based on Docker. So we wanted to build something around the same concept, and the main idea or the objective, it was to reuse what we did. So easily we can do something that the people can play, and we can do this meetup, so people come and have fun and all this stuff. So we started a group to discuss about it. We had a first meeting, and in the first meeting we decided that we are not going to do this. So why reuse what we did? Let's build a framework. Okay? So why we want a framework? We don't want to be building access to database. We don't want to be building front ends. We want to do the fun stuff. And where is the fun? In the games, in the challenge itself. So we can think a history. We can think about storytelling. We can think about the cool stuff. So we wanted something that we can reuse in the future. We can add more features, but the core, it's already done. Okay? And also because engineers like a lot the refactor. We didn't end what we are doing, so we want to refactor again. So that's the backend. So what we built, we built a backend that it's hosted in Amazon, and then we have the games that it's what you, I hope, download and play. Okay, so this is the architecture of the backend. So you can see basically we have the front end, that is a website that you were looking for the score. Then this front end, of course, communicates with a backend, that it's getting the information from the database, and it's also getting the solutions and the challenges from the solver. Okay? So what is a game for us? So we wanted to build something also that we can delegate to people to build games. So what we did is we created a framework an API so people can implement the games. We are talking about Shipstead. It's a big group, so we have many engineers. So we want everyone that we can building these challenges, not only us, because a lot of people have different ideas, and I'm sure that people will have awesome ideas for new challenges. So we wanted to simplify as much as we can, so we can onboard more people in this game. So a game is a solver. That maybe the name we need to change it because it's not just a solver, and also challenge. So what solver does? Solver is what it's in the backend, and it's responsible to generate a challenge. So for example, if I hope most of you play it, in the legs, for example, that we are solving mazes, we ask for a maze. Actually, we ask for a set of mazes, but we ask for a maze to solve it. So give me a maze. Then we have the game that solves the maze and sends the result to the backend. Okay? So a solver generates a maze and validates that the maze is actually okay, or it's not, or it's partially done, or it's partially solved. Then we have the challenge itself, that it's the code that you are downloading, you download from GitHub, and you fix to solve the challenge. So basically what the challenge does is get targets. In that case, we ask for robots to kill from in the weapon challenge, and then we send the evaluations. We send, okay, kill all these robots, and then the solver, as we saw, evaluates if it's right or it's wrong, and provides you, or if you remember, the score and how many robots you kill, how many allies you kill. How it works in the player computer. We have a game that wants to communicate with the backend. We wanted to implement a way that in the game we can keep the storytelling. So we don't have things like a slice challenge, a slice whatever. No, we want to keep something that we can have magic in the game. So the weapon asks for targets. He doesn't ask for a challenge, because what the hell is a challenge? So he asks for targets. Then we have this head component that if you play, you needed to fix something around this head, that it was a token. It's a spoiler for Gerard. That basically translates from the game to something that backend can understand. So in future games, we expect to have not another heads that translates from magic, from storytelling, to something that it's a standard. So you see that I'm doing this really fast because I don't want to take time from Gerard. That will be the fun part. But also I wanted to speak briefly about how we build this in the infrastructure part. So we are using the pipeline that we use the pipeline that we are using currently in infrastructure. So we have all the code in GitHub. When we did a commit, it triggers Travis build. So it gets the code, it passes the test. We had tests, some. Then whatever it does, the validations, it generates an IMEI. Okay, Amazon IMEI. As I said, it's everything working in IMEI inside in a container. So we have one instance, one container of the backend, one container, one instance, one container of the solver 1, solver 2, solver 3, solver 4. Then when we have the IMEI, in Travis, we deploy, in Asgard, we deploy this IMEI into Amazon Web Service. Okay? In other meetups, we explain it, and we will also explain again how Asgard works and all this stuff. But the intention of this meetup, as I said, it's the solution of the challenge. So basically, this is a pipeline, and this is some information about the challenge. Here you can see how many times we deploy each component. So the number, this 2. So you can see the front end, we deployed 22 times. But we didn't nail it at the first time. This is the analytics. So it wasn't that bad. We had many people interested. The last spike is from a Docker tweet. And this is the participation that we had. We had 120 tokens, 12 people solved the whole challenge, and 19 solved good enough to be here and get a prize. Well, everyone was invited, but these 19 will be applied for the prize. And basically that's it. I don't know if you have any question for the infrastructure. We can discuss it later, maybe, if you agree, and then we can let Gerard explain the solution. Yeah? Any question while Gerard gets ready? No? Good.
No, merci. Okay, so what we are going to do now is to really quickly go over all the challenges and solve them one by one. So really quickly, I promise. So those of you that didn't have the opportunity to play or to solve all of them will now know how we intended them to be done. We know that there's not just one solution. There are many of them for some challenges. And we also know that some of you have come up with really innovative solutions. So while I talk about some of the solutions, if you want to speak about the solution that you have implemented, you can do so. You just raise your hand and you feel free to interrupt me at any time. So right now, I'm just going to play as if I were a normal player. I'm going to register a new token. And we'll play the game. So okay, this is my token. I'm Judita. One fun thing is that all names are women's names. We didn't know that originally. We just downloaded a list of names and we looked at them really quickly and they seemed all right, but it turned out that it was a list of women's names. So yeah, okay. So as the instruction says, in order for the head to work, so I've downloaded the game and I've already built it, so you don't have to wait. But if you start the game, you will see that there's an error that says, okay, so the head is missing the robot identity. So where does the robot identity come from? From this DM2 token that we just got, right? So first, I'm going to open another tab here. Okay. So this goes to the Docker Compose YML file. Hopefully, you all got this far if you played the game. So this is the token. Oh, sorry. Demo effect. Okay, so now if we turn this down, we're going to kill it right up. Can you see the font? Yes, right? Yes. It's okay, okay. So now everything is working. When I say working, is that everything is giving errors. That's how it's intended. So we have many parts. We have the weapon, which is complaining. We have the arms, that it's complaining because it says that there's a bad file descriptor. We have the heart, that is unable to receive a heartbeat response. We have this part called the radio, which is giving a really weird message, but basically it says that there's some integrity message, which is wrong. We have the legs, that has something to do with mazes, right? Because it says you fell off the maze, you are lost in the maze. We also have the weapon, that we know that we destroyed all the enemies, right? And we destroyed all the allies too. Okay, so what is this about? So first, let us start by the easiest game. So if you go by the points, the heart is the easiest one. So let's do this. So the heart is telling us that it has a problem retrieving the heartbeat response. So let's see what this is. Let's go into the heart, for instance. And let's see what happens. So the heart, okay, has many components. But basically, we have a client that is very simple. Whoop. Okay, in black and white, sorry. So the heart does practically nothing. it only tries to communicate with the head. So we can see here that it retrieves the name of the head endpoint from an environment variable and tries to place a GET request. And if it fails to do so, it says unable to retrieve heartbeat response, which is the message that we see in the Docker Compose log. So OK, why is that happening? So if we checked, if we try to ping the head, OK, it isn't working. If we try to ping other parts of the robot, it isn't working. And we can guess that it should do so. So if we look at the network configuration, we can see that it's in a particular network, in this case. And if we look at other parts, specifically, for example, in the head, so we do this. Oh, no, it's Debian. OK. This? OK, yeah. OK, so it's in another network. So it's in the 20, and this is in the 21. So why is that happening? So maybe some of you were luckier and saw it at the first time. But if you look at the Docker Compose file, you can define different networks. And most of the parts, including the head, are in the internal network. But the heart one is in the external network. So if we change this and we put it in the internal network, we don't need this any longer. And if we try to start it again, let's see what we get. OK, so the heart is working. We have the heart working. So this is the easiest one, and hopefully we will appear in the scoreboard, I guess. Yeah, we are this one, or this one. I don't know. I guess this one, yeah. OK. So let's go with the arms, which is a little bit harder, but not too much. And the heart has, the arms, sorry. So the arms, why is it failing? So it is failing because it says that there's a bad file descriptor. So let's dive into the arms and let's see what happens. OK, so the arms, we can see that it only has 2 files, but let's do this. OK, so arms builds in the OPT path, and it only has 2 files. So the first one, engage, it only runs arms sh, and it then waits. So the trick will be in arms sh. So what is here? So we have some instructions that the doctor has left for us. And it says that the module verifies that the arms can solve problems in coordination with the head and the tools present in the robot, which we don't know what are. So the verification is successful when our mate-in-one puzzles are successfully solved. So we can guess that it will have something to do with chess, but we don't know how this works. So if we look at the script, we can see that it fails when there's the first error, and it tries to connect to the head. And the way it does it is by using a bash feature that allows you to use TCP connections, or, well, network connections as if were files. And you can then open them and pipe to them and pipe from them and, well, basically use the file descriptor as if it were a file. So, well, or really a socket. Well, OK. Then it says that it retrieves the puzzle, and it reads puzzles from this connection. And then you can see that there are other file descriptors that are used, which is the number 9, right? And it's the one that is giving the error. So 9 bad file descriptor. And it's normal that it gives this error because we aren't opening this file descriptor. This file descriptor is not defined anywhere. But what should this do? So first, we'll try to connect to this. So this is connecting to the head at the port 7777. So let's try to connect there. So let's see what happens. OK. So we receive this. We receive some weird lines, and then end of file. So these lines, if you Google for a bit, you'll see that it's FEN notation, which is a kind of notation that defines the board state in a chess game. So why is this? Well, this goes a little bit with the theme. We know that we are trying to solve chess puzzles. And here, we see that we send some information to this 9 file descriptor, and we see position FEN, which is this type of strings, and then it passes the strings one by one in this while loop, right? So if you Google these commands, you will see that these are commands which are compatible with the UC chess engine standard. And if you look for this type of chess engines, you will find one, which is Stockfish, which is a very famous one, which is open source. And if you look at the, at the DockerMaze, you'll find here work DockerMaze. Okay, you'll find that there's a container that is called actually Stockfish. So okay, what is this? Let's find out. Okay, so okay, we have this stockfish SH, and if we look at this, we'll see that it's listening at port 9999, and it's just taking whatever is received through that port and passing it to the stockfish binary. So those were stockfish commands, and they are passed to this port. So maybe if we just plug it, it will work. Let's try that. So if you look at the arms, and we just open another file descriptor, which connects to the stockfish engine to the port 9999. And if we execute the arms, again, you get all puzzle solved, and then you're successful. And let's see. Yeah, who are we? Yeah, okay, we are here. Next one, the radio. The radio is quite a jump in complexity, but it's not as hard as it seems. Okay. Let's see. Let's do this. Okay, so the radio one. So the radio one is harder to do from the inside, as I've done the other ones. I like to do them from the inside, but because it uses another user which doesn't have privileges to look at all the files, so I will do it from the outside since you have the source code. So let's look at the radio. So the radio has many files. Has this first one, which is the compile.sh, that basically compiles a source file, which we'll look at in a little bit, as create Mac, which is a binary. Okay, and then we have the radio.com, which is a Ruby client, which basically the important part is that it creates the Mac with the create Mac binary. So we know that the Mac was failing. So we can guess that this create binary will be wrong. So let's look at the source code, and we find a surprise, which is that it's in assembler. So this is basically Intel 32-bit assembler, and what it's doing is that it's taking the whole message, it's encrypting it it's performing an XOR operation with this key, and then it's calculating an integrity checksum, and the way it does it, we can see it here, is with this create Mac function, which just takes each byte and XORs it with the next one, and then the accumulated XOR is the checksum, so it's just 1 byte. So this function is implemented in C, but here we see it in assembler, and it's missing some parts, specifically this part. And here it says, here I guess I should add the code responsible for getting the current byte and XOR it with the accumulated Mac. Okay, so we are going to solve this in one sit, because the thing with this challenge is that you have to learn at least a little bit of assembler to solve it. But once you look at it, it's really not that hard. But here, the thing that you have to do, basically, so you have the accumulated Mac in this memory position, and you have the current position in EAX. But it says that EAX points to that current position, so we don't have to use the EAX register. We have to use it between brackets, but because that means that we are using whatever is in that memory location. So what we would like to do is to just XOR whatever is in the EAX position with the accumulated Mac, but we cannot do so because the XOR operation cannot take 2 memory addresses. So what we need to do is to use a temporary register to store 1 variable and then do the XOR. So what we can do, for instance, is to use EBX. But since we don't want to mess with the program, we will back up EBX by pushing it to the stack. And then we'll push it to the stack. We will move. Yeah, I'm sorry. So
maybe if you could change the background.
You cannot see it. Yeah. Sorry? Okay, but it will look. Okay, if it has improved for you, you cannot see. It's fine for me, but let me see. Okay. Is this better? Okay. So we will move EX to a temporary variable. So what we will do is just use 1 byte. Because we just need 1 byte, because we need the byte of the current position, and the Mac is just 1 byte. So we will use BL, which is the lower part of the register, because we don't need the rest. And then, yes, we can XOR BL with the first byte at this address. And then we need to pop again EBX because we pushed to the stack to back it up. What did I? Oh, sorry, typo. Yes, OK. So that will hopefully work. Let's see. So we need to rebuild because we have changed a file from the source. So we will build it again. This was too fast. OK. Let's see. Yeah, recreating radio. OK, and the radio is working. The Mac is created all right. So now we can see that we are pretty up in the scoreboard, but we are aiming for first. So now we just have 2 challenges left, the weapon and the legs. So first with the weapon. So the weapon is this one. And the thing is that we are killing too many allies. We are destroying all the enemies. That we do all right, but we are killing all the allies, so that's not good. So what we will do is to dive in. OK, and see what's wrong. So as you have realized, many challenges are an OPT, but there's no reason why. So if you look at there is just 2 files that are meaningful. So this one that just executes OPT weapon, and if it is not running, if it doesn't exist, it will compile it again and run it again. There's the binary, the weapon. OK, well, never mind. And then we have the source code. So, OK, we have some instructions. And it says that to win this challenge, you have to destroy as many enemies as possible, and you have to spare as many allies as possible. So here says death to the red robots. So the enemies, we can gather that they are the red robots. So now we have some comments down here. If we uncomment this, you will have some meaningful information. Let's see what's going on this game. We need some additional packages to print. OK. So if I delete the binary, it will execute again, hopefully. Yes, and it's executing again. And it's printing us some debug information. So now we can see what the challenges are. So for example, we have this URL, which is a challenge, and the program has decided to destroy this robot, which is not a red one. Then we can see in the histogram, which I don't know if it's the one that, yeah, it's the one that goes before, that we have so a histogram is a representation of an image, of the colors of an image. So we can see the different colors and the different intensity levels. So you can realize, for instance, let me look at an image that hopefully will be red. So for instance, this one has a lot of red, but has a lot of green also. So I guess it could be purple. Let's see. So as you may have realized, by looking at the histogram, you can tell a lot about, no, it's green, OK. You can tell a lot about the image. So the goal of this challenge is to understand how histograms work and how you can use the information displayed in the histogram to decide if a robot is blue or if the robot is red, green, yellow. So there are 2 challenges. First, understand how to use this information. And second, be able to differentiate red robots from orange ones and purple ones and brown ones, which also have a huge amount of red in them. So we could think of a very naive solution. Let's see if it works, which could be, for instance, because you can see that the most meaningful value of the histogram for us is this last value. Because the others are pretty equal, but there is where we see the difference, because it's the more bright colors, which the robots, if you look at them, they are very bright. So we could look just at the last number and try to guess what happens. So maybe we could do something. So here you see at the code, it's just destroying all robots, if true, destroy. So we can do something else. So the histogram is passed to this function, so you could take the histogram and take just the last value, the highest intensity. This is red, and say that the red at the highest intensity should be larger than the green at the highest intensity. plus plus the histogram plus the blue at the highest intensity. So let's see if this works. So we remove the binary, and let's see what happens. Okay, so we did somewhat better. We scored 28%, but even though we still destroyed almost all of the enemies, we still destroyed many allies. So another solution would be to balance everything. So now we will take into account all intensities, but we will just take into account, we will take more into account higher intensities than lower intensities. So let's try with this. So okay, let's take the weapon code, and let's just build a loop that will take like this, for instance, for I. Okay, so now we'll take, we'll define the variables first better. So as integers, and then we'll take red, and we will add for each intensity level the amount of color for that intensity corresponding to the red times I. And that is a very simple way of balancing colors by intensity. So we will do the same for R, G, and B. And then instead of comparing just the last one, we will compare the values for R, G, and B. And let's see if we are doing any better. So we can remove the binary now and see what happens. Oh. Okay, we're doing much better. Now we have actually passed the challenge, but only with 71% score. It says that we have medium collateral damage, because you can see that even though we destroyed all the enemies, we still destroyed some of the allies. So now it's just a matter of fine-tuning the algorithm. So one way of doing that, for instance, is to add just a factor. What I did was add a 1.5 factor. And now, since you are using float numbers, you have to cast this to float. And I found this to work pretty well. For the challenge, we generated 600,000 images, 600,000 robots, and this algorithm fails with 40 or so. So, but one of those. Okay. Okay, now it should work. Now it should work with 100%, if I'm not wrong. Okay, yes, okay. Okay, so now it works. So we are left with just one challenge. If we look at the scoreboard.
This was easier than the sample one, right?
Yeah. So we are at the scoreboard around, where are we? We are here. Oh, what? Ah, weapon is last. Ah, okay. Didn't the order change? Wasn't it? Oh, okay, okay. Well, now we are going to do the legs, which is the last one. I'm going to do it really quick because it's very easy. No, I'm kidding. So, okay. So let's do the legs one. We're doing it from the inside. So DockerExec, IT, legs. Okay. So we have this. So what we have is a walk script that does something that just executes the Maze client and then sleeps. So the Maze client, what is the Maze client? It's a command. So where is it? Okay, so can we look at this? Here's a local bin Maze challenge. Okay, it's a Python script. And we can see, not to beat around the bush too much, that we have a setup script, and then we have the client here. So what the client does, well, here we have the rules explained in a lot of detail, courtesy of Danny. So basically what this says is that you will have different mazes with different complexity, and you have to solve them. And they will take into account how optimal is the path that you can get to solve them. So this client works along with a library, which is called Maze Solver, which you can see here. And well, it just calls the function solve maze of the class Maze Solver. So we can look at this library and see what it does. So here is the code that actually solves the mazes, which isn't working right now, because as we see, we fell off most of mazes or we got lost in the mazes. And this is a very simple solver. As you can see, it's very short. And what it does is that it implements a very naive algorithm, which is that given any two-dimensional maze, you can get out of the maze just taking your hand, placing it on the right wall, and just walking along and never letting go. So you will eventually go out of the maze. So that is a solution that works for all mazes, and that's what this algorithm implements. So what you have to do is, to teach it to a computer, you have to teach him that to always go to the right if it's possible. If not, you go to front. If not, left. If not, down. So if you look closely, you can see that the directions are defined left, up, left again, and down, which is wrong. And in the code, they are implemented as so. But as we know, the algorithm is always going to the right or always going to the left, but you have to go in order to all the 4 directions. So we are going to try and change this first one just to be right, which is what we think should be. And then we can install again by running Python setup install and run the Maze client, which will hopefully now work. Too much energy. Okay, so we are solving the mazes. You are escaping alive, but it says that too much energy was wasted. And that is because this algorithm is very naive, and even though you can get out of the maze by doing this trick of always going to the right, you will have to walk almost the whole maze to get out. So there are more algorithms that are optimal, and one of them, if you Google this, it's A star, which is an algorithm that works differently with distances and so on, which uses backtracking to see if a path could have been done faster. So what I did personally, yes.
Or if you did it in college and you listened.
Yeah, but I didn't go.
It can be Google or you can actually listen.
Yeah. Okay, but some of you actually coded them from scratch, so kudos. But I did some Stack Overflow oriented programming, and I found this, which is, it was okay. I like this. So I found this link, which basically implements A star in Python to solve ASCII mazes like the ones we have. So I thought, oh yeah, so lucky. I will just be able to copy the code and use this, and I will have one. But no, because what it does is that instead of giving you the directions you have to walk, it solves the maze and it paints the path. So okay, that wasn't working because in order to beat the challenge, you have to respond with all the directions that you have to go. So what I did was copy this and then have it solve the maze, and then just walk through the solution and notice the directions that you have to go. So the cool thing about doing that is that my solution actually paints the maze, which looks cool. So I'm just going to copy it because so I'm going to copy this to the clipboard, and then go to the maze lib. I'm going to, you know how to delete everything in BI.
You can put a big number and it
No, but in BI, not in.
You can use the number of lines into the list.
Okay. Okay. Well.
And you will type
Done. Okay, so now we have it. Let's see if this works. So now we have to install again. Okay, and now we will run the solution and see how it looks. It's cool, I think. So now we have. So yeah, now you skip the maze and he says full energy level, great. So now this is the last challenge, and hopefully we will be first on the scoreboard. Well, first, I don't know if first, but Judith. Yeah. So yeah, that's it, finished. Thank you.